I'm Larrabee Strow. I'm a professor of physics at the University of Maryland, Baltimore County, and I've been working for the last 30 years on high-resolution spectroscopy related to the atmosphere. High-resolution spectroscopy is the study of how radiation interacts with the small molecules in the atmosphere and how they interact with the collisions and with temperature and various other parameters. Well, a lot of the basics of high-resolution spectroscopy comes from laboratory measurements, which is what I did for the first 20 years of my career. And we either used instruments like airs, except they were in the lab, or lasers, and we would shoot radiation through gas cells and then study how it absorbs the radiation as a function of temperature and pressure, trying to simulate the atmosphere. And then we use that data to improve our theoretical understanding of the molecular radiation spectroscopy, which we now use to analyze the airs data. Well, with the new instruments that are coming online like airs being the first one, we get thousands and thousands of different wavelengths of light at this one time when we measure the upwelling radiation from the Earth. And it forces us to really understand how the molecules interact with radiation to produce those radiances. And it's a different game than we had to play 30 years ago, 20 years ago. And it's been a goal of NASA for quite a few years to measure minor gases from orbit. And there's always been ideas for specialized instruments, but we've never really, until very recently, had any instruments that could measure them down into the troposphere. We concentrated instead on the stratosphere. And these days, trying to understand tropospheric chemistry is really one of the premier goals of NASA. And when the airs idea was developed, it was actually quite trivial to go there and understand that it could measure some of the basic gases, especially carbon monoxide, just from looking at the instrument design and understanding the spectroscopy involved. What we didn't understand is that we could measure some of the other minor gases so well, such as methane, and more recently we're looking at nitric acid and some of the chlorofluorocarbons. In the atmosphere, every molecule has its own signature. And so that's one of the beauties of a hyperspectral instrument such as airs, is that by having many, many wavelengths, some wavelengths are sensitive to carbon dioxide, some are sensitive to carbon monoxide, methane, and so on. Now, there's a lot of times when they overlap with each other, but because airs has so many thousands of channels, we can generally separate out those interferences. So by looking at different wavelengths of light, or infrared light with airs, we can separate out the effects of the different molecules. Molecular spectroscopy studies the interaction of the molecules with radiation in terms of how well they absorb or they emit. When we do radiative transfer, what we have to do then is we have to say the radiation that the molecule emits takes a path from where it emitted it in the atmosphere up through the atmosphere to outside the atmosphere to the airs instrument in space. And the radiative transfer then is properly calculating that transfer of those photons, because they are continuously being absorbed by other gases in the atmosphere, re-emitted, absorbed, re-emitted. And so the radiative transfer has to take all those absorptions and re-emissions as the radiation travels, let's say, from the surface to the airs, into account. The other thing, and where a lot of effort goes into, is we have to make those calculations extremely fast, and I would say half of our effort is computational issues in order to make this work fast, because it's a mountain of data that you have to go through every day, and you can't afford computers to do it in more traditional ways that we would have done in the laboratory. Well, I have a couple things I'm after. Some of my goals are just to make airs products the best they can be. What I do is I produce the algorithm that calculates what air sees. And so you take what air sees, you take the code that we write, which is the radiative transfer code, you change the atmospheric parameters in that code until you get agreement with the airs observations. So that's kind of my tool that I produce. What I'm interested in more theoretically is to understand the spectroscopy of the atmosphere better using airs. Airs is a spectrometer, and we use it to do fundamental spectroscopy. We've done a lot of that during the airs validation program. I'm also interested in measuring minor gases with airs, such as carbon dioxide, methane, more recently nitric acid, things that we didn't even assume we were going to be able to measure. And in fact, my initial reason for getting involved with airs was to measure carbon monoxide. Well, I think that, of course, airs is well known as a weather instrument. My primary scientific goals, though, are for climate. And the really key thing I want to do is to see if the airs radiances, the raw fundamental thing it measures, can eventually be used to understand climate without all the complications of turning it into atmospheric parameters. There's a history of that with some that people have been working on with previous instruments that were flown in the 70s. And kind of what my goal is to start with airs and go forward with the operational instruments that are going to build on top of airs and see if we can build a climate record of over 20, 30 years that no one can question because it's a fundamental measurement of a calibrated instrument, and it'll be unequivocal what the answers are. The whole reason that I joined NASA was to work with satellite data. It gives you a global picture. It makes you feel like you're really doing something important because you see the whole planet and you see it from pole to pole. You see it around the whole world. And if you really want to answer some important questions, you've got to look at global data, and that's why I like working with satellites.